I'm Ben-Yaakov. This presentation is entitled A Supplement to Resolving a Current Control Mystery in PWM Converters. This is actually an addition to a video that I have posted recently in my YouTube channel. This is the link to the video. I'm going to print it also on the page of this video that you are now watching. And the original video was entitled Resolving a Current Control Mystery in PWM Converters, in which I've posed a question and tried to explain how is a current changing in PWM converters. Following the posting of the video, I got a number of comments. Some agreed with my explanation, some, however, had some doubts. So the purpose of this supplement is really to explain some points that perhaps I've missed in the first video, and actually answering some specific questions that some people have brought up. So let me first of all go very quickly over the original content or summary of what I've covered in the original video. And the question was like that: if I have a, say, bidirectional buck boost converter, that is, it's like this way it's a buck and this way it's a boost, it's of course synchronous converters, and current can therefore flow one way and the other. Now if we look at the textbook expression for the duty cycle on each case, we come up with expression that shows that the duty cycle of these switches, that is the time they are on and off, are exactly the same both for one direction of current and the other direction of the current. And my question was, what makes the current change direction? If the duty cycle are the same, the time that this transistor is on and this transistor is on too and off, etc., are the same, so why would the current go this way or the other way? This was the original question. And you can have it in many cases. For example, here, this is a power factor correction. We know that we have actually a boost converter. This is a boost converter, but we change the current such that it'll be sort of have a rectified sinusoidal shape, so that at the input we'll have a sinusoidal waveform of the current. And the question was again, if this is a boost converter, the transfer ratio between V in and V out is this one, and it's dependent any given instant on V in, but what makes the current change? Why is it not constant? Okay, so these were the questions, and my explanation was that this textbook expression for, say, a buck converter saying that V out is D times V in is an approximation, and there is something hidden here which we normally don't pay attention to. And that is that there is a need for some change, some incremental change in the duty cycle in order to make the current change or go one direction or another. And to explain it, I am showing here that I can represent the voltage drop on the parasitic resistance, say here. I'm neglecting other parasitics, okay? I'm just talking about this parasitic resistance. I can represent it as a voltage drop. So therefore, the duty cycle required is not just V in, V out, but either plus or minus this voltage drop. So you have to modify it. So one direction, the duty cycle will be a bit larger, and the other direction will be a little bit smaller, and this is actually enhancing the current to go one direction or another and overcomes the voltage drop of the resistor. And the same thing goes here. In the case of the power factor correction, the duty cycle to be developed by the feedback is not exactly according to this boost equation, but there is some delta here which will cause the current to increase, and therefore we can control it in such a way that it will follow the reference that we have here. And the conclusion was that the textbook expression of PWM converter transfer function really do not explain the change in current, and the current changes are caused by deviation from the classical duty cycle expressions, And these deviations are automatically taken care of by the controller. So this was the content of the previous video. So now one of the viewers brought up a kind of interesting question. So what happens if there is no parasitic resistance? So the whole story of resistance, voltage drop, etc. is irrelevant here. So let's have a look closer what is really happening in this case, and then we'll expand it to the practical case with a resistance, because obviously this is a theoretical question here. There's no system on Earth without any parasitic resistance. But nonetheless, just to explain the point here, let me start with an ideal system. Here we have the pulses representing the, say in the case of a buck, the two transistor switching. We have an inductor, no resistances, then we have an output voltage here, okay? And we can represent it as an average voltage here, which is the average voltage here, and an average voltage here, and an inductor. This could be just two voltage sources, which are equal. And here comes the question. What will be the current in this case? Well, I don't know if many people watching now this video have ever considered a question like that. Well, there's no answer here. This is an undetermined case. The current can go one direction, it can go the other direction, it can be high, it can be low, it depending on the initial condition, and then it'll go forever. And this is exactly the case if you have an inductor with a current and you make a short on it. The current will continue continuously because the voltage across it is zero, and therefore the IDT is zero, so it'll just go on forever. And exactly is this case here. The voltage across the inductor is zero, the IDT is zero, so whatever the initial condition was here, it'll continue. So this is an undetermined case. You cannot tell by knowing these two voltages and inductor what will be the current. Now let's turn to a converter. And let's assume for a second that it has no parasitic resistances whatsoever, but it is in closed loop, such that the voltage at the output is kept constant. So we have now a microscopic view of the situation. We have these pulses coming here from the two transistors, say it's a buck converter, and as a result we have the current going up and down, up and down. This is the ripple on the current here. The slopes are related to the voltage difference on the inductor. The maximum voltage here is V in, so it'll be V in minus V out over L. This will be this slope here, and this slope here, the down slope will be minus V out over L. I'm neglecting, again, voltage dropping. This is an ideal case that there are no resistances, voltage drops whatsoever. Okay, so this is sort of goes forever. This is the duty cycle, this is the current, and here I'm showing the output current. This is the current, this current here, IRL, and this is the output voltage. Okay. Let us now assume that there is a change in RL, smaller resistance, higher current, and here I'm showing it like this. And therefore, since there is an imbalance now between the current here and the current in, the average current, there'll be a voltage drop here. Here is the voltage drop at the output. This will be sensed by the amplifier, and momentarily the duty cycle will increase. This increase in duty cycle will change the time here and will cause the current to go higher. Then this could be enough, and then it will go on as before, except that the level now is higher. Since V out and V in are the same, therefore the slopes are the same, and everything looks the same except that there was a jump here due to this delta momentarily incremental increase in the duty cycle, and this here we have a new situation. Now obviously this is a very theoretical and impossible case because there is no such thing as a converter without parasitic resistances. So what happens if there is a resistance, okay, which is the realistic case? In this case, if there is a change in the current due to this change in the load resistance, again we're going to have a drop here. Again, we are going to have an incremental change in duty cycle, but then we need an extra change in duty cycle to come over the voltage drop here. That is, we need a somewhat larger duty cycle because now it's V out plus some voltage which is a bit higher than it was before. So this incremental, momentarily change in duty cycle will just bring it up, but then this deviation due to the voltage drop here will continue, and the picture will be sort of looks like about the same. So this is really the explanation of what will happen with an ideal case in which there is no resistance at all, and the case in which there is parasitic resistance and there will be a modification of the duty cycle by the feedback, keeping the V out to be again constant. So this is the end of this very short presentation. I thank you very much for your attention. I hope you found it interesting. Thank you very much.